are going to learn about forced oscillation or driven oscillation. We have studied in a pure simple harmonic motion, the amplitude remains constant throughout. In damped simple harmonic motion, the amplitude goes on decreasing with time, and it is due to some damping forces like air resistance, frictional force, viscous force, etc. Now, in forced oscillation, in order to maintain the amplitude, what happens if an external force is given periodically? The amplitude can be maintained or amplitude can be increased also. So, such oscillations are called forced oscillations or driven oscillations. Okay. So, if the amplitude decreases with the time, that is called a damped oscillation. And in damped oscillation, if an external force is given periodically, okay, whenever the amplitude decreases, if you given an external force periodically, the amplitude can be maintained. And such type of oscillations are called forced oscillations or driven oscillations. When a system such as simple pendulum or a block attached to a spring is displaced from its equilibrium position and released, it oscillates with a natural frequency. This is a pure simple harmonic motion. All free oscillations eventually die out because of the damping force like friction, air resistance, etc. And this about the damped simple harmonic motion. But if an external force or external agency can maintain these oscillations, and such oscillations are called forced or driven. Okay. So, if amplitude decreases and an external force is given periodically, the amplitude can be maintained or it can be increased, and such oscillations are called forced or driven oscillation. In the case of simple pendulum, if simple pendulum is oscillating between the two extreme positions, what happens? Its amplitude goes on decreasing. Okay, with the time amplitude goes on decreasing, and such oscillations are called damped. And whenever the amplitude decrease, if you give an external force, okay, just you push the bob periodically, what happens? Amplitude can be maintained, and such oscillations are called driven. Most familiar example of forced oscillation is when a child is in the garden swing, periodically presses his feet against the ground to maintain oscillation. Okay, when a child in the garden swing periodically presses his feet against the ground periodically to maintain the oscillation. So, if the child is swinging, the child usually presses the ground periodically, and by doing so amplitude can be maintained and amplitude can be increased also. And this is the best example for forced or driven oscillation. Here the forces acting are the normal restoring force, which is given by F equal to minus Kx, F equal to Ma, then damping force Fd equal to minus Pv, and an additional force which is given periodically, and that force is called driving force, and it is given by the formula F0 cos omega dt. You have to by heart all the values. So, driving force is given by F equal to F0 cos omega dt. So, this cos omega dt shows that the driving force is given periodically. So, that external force is given periodically, and hence there is cos function. So, there are four forces here in a driven simple harmonic motion or driven oscillation. What are they? F equal to minus Kx, F equal to Ma, damping force Fd equal to minus Bv, and the driving force F equal to F0 cos omega dt. Now, we can equate here Ma equal to minus Kx minus Bv plus F0 cos omega dt. Why here it is negative minus Bv? It is negative, which shows that damping force opposes the motion. Here driving force is positive because it supports the motion. It is in the direction of motion, oscillation. Okay, it always supports the oscillation. And here acceleration is d square x by dt square. Therefore, we can write m into d square x by dt square plus kx plus b into velocity is dx by dt plus f0 cos omega dt equal to 0. We can divide the whole equation by m. We can write d square x by dt square plus b by m into dx by dt plus k by m into x plus f0 by m cos omega dt equal to 0, and this is the differential equation of a driven simple harmonic motion. So, what is the differential equation of driven simple harmonic motion? D square x by dt square plus b by m into dx by dt plus k by m into x plus f0 by m cos omega dt equal to 0. Here omega d represents the driving frequency or driven frequency, that frequency of the external force. Okay, that frequency is omega d. Now from this equation we can write the differential equation for a damped simple harmonic. Damped simple harmonic motion, there is no term like this. So there is no driving force. So this term will be absent in the case of damped simple harmonic motion. In the case of pure simple harmonic motion, damping force is also absent. So d square x by dt square plus k by m into x is equal to 0. That is the differential equation of a pure simple harmonic motion. Okay, in a driven simple harmonic motion, there are 4 terms: d square x by dt square plus b by m into dx by dt plus k by m into x plus f0 by m cos omega dt equal to 0, and this represents the differential equation of a forced oscillation. The solution of the differential equation is x equal to a cos omega dt plus phi. Here omega d represents the angular frequency of the driving force, that external force. So the solution is x equal to a cos omega dt plus phi. So amplitude A is f0 divided by m square into omega square minus omega d square the whole square plus omega d square the whole raised to 1 by 2. Actually here m represents the mass, omega represents the natural frequency, omega d represents the frequency of the driving force, and b is the damping constant. So here amplitude is, this is the value of amplitude. So this is similar to a pure simple harmonic motion. Have you remember? So the in a pure simple harmonic motion is x equal to, solution is x equal to a cos omega t plus phi. There a is simply a, but here in the case of forced oscillation, x equal to a cos omega dt plus phi, and here the a, the value of a is, this is the value of a, that is f0 divided by this much value. Okay children? So we know amplitude of a driven simple harmonic motion is a equal f0 divided by m square into omega square minus omega d square the whole square plus omega d square b square the whole raised to 1 by 2. If omega and omega d are equal, omega represents the natural frequency, omega d represents the frequency of the driving force. If both the frequency are equal, omega and omega d are equal, what happens to amplitude A? Amplitude A becomes, this term becomes 0, isn't it? So amplitude A becomes f0 divided by omega d square b square the whole raised to 1 by 2, that is omega d into b. Clear? So if the natural frequency omega and the driven frequency omega d are equal, amplitude becomes f0 divided by omega d into b. That means amplitude is maximum. So what is the condition for maximum amplitude? If the natural frequency and the driven frequency or the frequency of the driving force, both the frequencies are equal, then the amplitude becomes maximum. So the phenomenon of increase in amplitude when the driving force frequency is close to the natural frequency, and this is called the resonance. So what is the condition for resonance? If the natural frequency and the driving frequency are equal, what happens to amplitude? Amplitude becomes maximum, and this condition is called the resonance. Resonance is a very important term and it's a very important condition. You have to study this resonance condition in 12th classes also. Okay, so what is the condition for resonance? If the natural frequency of a system and the driven frequency both are equal, what happens to amplitude? Amplitude becomes maximum, and this condition is called a resonance. And in our daily life, we encounter this phenomenon of resonance in so many situations. For example, we know that in moving swing, if a child in the garden, the child is swinging in the garden swing, and he usually presses the ground periodically. So by pressing the ground periodically, if that frequency, pressing the ground periodically means it is a periodical motion, it has some frequency, that is a applied frequency, driven frequency, and the swing has its own natural frequency. If both the frequencies are equal, what happens to amplitude of oscillation of the swing? It will be maximum. Okay, so the maximum, the child can move with a maximum height. How? Because by by the condition of resonance. If the condition of resonance, that means by pushing the ground periodically, it has a frequency. That frequency is the driving frequency, and the swing has its own frequency, and that frequency is the natural frequency. If both the frequencies are equal, which condition is satisfied? Resonance condition is satisfied, and the amplitude of oscillation will be maximum. Okay. Some general examples for resonance are: soldiers go outer steps while crossing a suspension bridge. So soldiers are asked to go outer step while crossing a suspension bridge. This is because if the natural frequency of the suspension bridge accidentally matches with the marching frequency, a resonance condition is satisfied and the bridge may collapse. So suspension bridge has its own frequency, that is a natural frequency. So marching of the soldiers, it has a definite frequency. If both the frequencies are accidentally matches or accidentally equal, which condition is satisfied? Resonance condition is satisfied, amplitude of oscillation increases and the bridge may collapse. And that is the reason why soldiers go out of steps while crossing a bridge. Another example for resonance is: an earthquake will not cause uniform damage to all the buildings in an affected area, even if they are built with same strength and same materials. The natural frequency of a building, it depends on height and other size parameters. So if a building has a natural frequency and the natural frequency of the building is nearly close to the seismic wave frequency, earthquake waves are called seismic waves, and it has a natural frequency, it has a definite frequency. If the natural frequency of the building is nearly equal to the seismic wave frequency, such buildings will be affected more. Okay, so buildings having the natural frequency very much close to the seismic wave frequency, such buildings will be affected more. Okay, and that is the reason why earthquake will not cause uniform damage to all the buildings in an affected area. So these are some common examples for resonance. So what is the condition for resonance? Once more, if the natural frequency of the system, oscillating system, is close to the driving frequency, both the frequencies are equal, what happens? Amplitude will be maximum, and this condition is called the resonance. Okay children?